interface products. So it is a fast growing research area nowadays. Brain computer interface means without any physical intervention, the brain signals that can be translated into commands. That is called as a brain computer interface. Thank you, madam. Now, if you look into the brain computer interface model, for example, let us take this is one person. Here is sitting here. Now, we will take the data. We have to perform some operations like pre-processing, feature extraction. We use some algorithms. Then finally, that will be translated into commands like here. Then again, the commands that will be given to this particular person as a feedback mechanism. These are the basic components. What are the basic components? One is data acquisition system, processing, feature extraction, using of innovative algorithms. Then that will be translated into the commands. These are the basic components in the brain computer interface system. Now, once again, I will come back to starting point. Here we have a brain. Now we are taking the data. As we mentioned earlier, we are taking the data here. How we are going to take the data? Data acquisition system means how we are going to take the data? Means we are going to take the data by using one particular device. The device is called as EEG, electroencephalography. We can use some other device also, but here in our topic, we are using EEG device. EEG stands for electroencephalography. Now, whatever the signals that are taking from brain, it is a way cannot directly give it to the computer and give translate in the commands. It is not like that. Why? Because brain is a complex machine in the world. Most complex machine in the world is brain. Already we know that. So it has a lot of signals. We cannot identify that signals, which signal belongs to which type of commands, which signal gives. So for that, we have to carefully pre-process that signals. We have to carefully pre-process the signals. So how we are going to pre-process the signals? Using some filtering techniques. What are the filtering techniques we are going to use? Here, we already know what are the filtering. As an electronics engineer or computer engineer, we already know. There are some low pass filters, high pass filters, some different innovative algorithms are there, some different Chebyshev filters, some IR filter, FR filters. There are different types of filters are there. But it is not a simple filter we are not going to use. Some innovative filter we have to use. That is the first step, first time, foremost thing in after taking the data. After taking the data, first we have to clean the data. That cleaning step is known as pre-processing. That clean step, cleaning of the data, is known as pre-processing. Then after that, we have to extract the signals. We have to extract the features. Features means it is not general features. So this whatever the taking the data that is in the time domain, that whatever the data we have taken that is in the time domain. Now the time domain signals we have to convert into the frequency domain. We already know what type of techniques we can use to convert this time domain signal into frequency domain. We have a lot of techniques, Fourier transform, Fourier series, some different transform, or DFT, FFT. There are different techniques are there to convert time domain into frequency domain. Now, in the frequency domain, what are the features we are going to extract? Like PSD, mean, if it is a time domain, mean. If it is a frequency domain, we have to take power spectral density, autocorrelation function. Like that, we have to take some features from the each after extraction. Then After taking some features, we have to apply some algorithms. Now, usually as a brain computer academic scientist, we naturally work in this particular area. What area? This developing some algorithm to classify the signals. That is the one particular area we can work on it. This is the one best part we can utilize for our research. Are you getting my point? Is it clear? Any doubts here? Am I audible? Okay. Yes. Please give your response. Start at least.
Audible, sir.
Okay. Thank you, madam. Now we have to use some algorithms, efficient algorithms, like some machine learning algorithms, artificial intelligence algorithms, some deep learning models we have to use for classification of signals. What type of signal we have extracted from the brain, like that, we have to use. That signals will be translated into the commands like visualization here, sound sonification, artification, haptic and tactile stimulus, olfactory stimulation, like this, which can be used for different applications. These brain signals that can be translated into the commands. In that way, we can use this particular signals. Now, this is regarding the brain-computer interface model. There are different blocks. Here I have explained different blocks. Now, after that, here, these, whatever the signals that will be again given the feedback to the particular person. Why? Because to improve that particular thing. Now, here, how your brain computer interface works. Here, brain computer interface, here it will works for the person. Here, the patient mentally visualize both hands closing. So there are different paradigms are there. How brain-computer interface works means here there are different paradigms are there that I will explain later. Now, first and foremost is here I will explain what here brain-computer interface here how it works means here. For example, here one particular person sitting in front of the computer who is unable to move his hand or leg, then what he will think that here, okay, I'm moving my leg like this. Here, he is a person, is a one person, is just sitting in front of the computer, and he think that I'm moving my left hand. Is thinking. The patient mentally visualizes both hands are closing like that. Both hands are closing. When he feels both hands are closing, then it generates one particular type of signal. When that particular person, when he releases that, he mentally visualizes, releases that particular hands. At that in that particular point also, here that will be another thing here. It also generates that type of signals like that. Now, what are the brain-computer interface approaches? What are the brain-computer interface approaches? Here, brain-computer interface. What are the brain-computer interface approaches? Here, there are different types of brain-computer interfaces. Here, one is invasive, semi-invasive, non-invasive. There are three different types of brain-computer interface approaches. Invasive means that whatever the person who is undergone that particular brain computer interface experiment, uh, he has to go for neurological surgery. That means some brain, they will generally implant electrodes inside the brain. That is called as a invasive. That means inside there is some, we need to do some surgery, some specific surgery for that person. That is called as a invasive BCI. Next, semi-invasive. Semi-invasive means on the scalp, they implant some electrodes. That is called as a uh, semi-invasive. They will use some, they will just some types of pins they will keep inside your brain, just implant. They are not, we will not go for any surgery, but they will implant some type of pins inside, implant inside the your brain. That is one, that is semi-invasive. Next, another type is non-invasive. That is another thing is non-invasive. Non-invasive means here that particular person here we are unable to they will just keep on the brain, but there is no, they will not implant anything on the inside the brain. That is called as a non-invasive BCI approach. That is another type of approach. These are the three different type of approaches. One is invasive, another one is semi-invasive, another one is non-invasive. Here, in the invasive means some surgery, semi-invasive means some implant, non-invasive means some MRI, EEG. These are the things we are going to use. Now, invasive brain-computer interface. What is invasive brain-computer interface? Invasive BCI involve implanting electrodes. Already, I just now discussed. So we have to implant some type of. We have to implant electrodes directly into the brain. That is called as a invasive BCI. What are the applications of invasive brain-computer interface? Restoring motor function, example, controlling prosthetic limbs for paralyzed individuals, therapeutic uses, advanced communication for locked-in patients. In that particular cases, we have to use this invasive brain-computer interfaces. Next, another one is semi-invasive and non-invasive. Semi-invasive means electrodes are placed under the skull but not inside the brain tissue. This is called as semi-invasive BCI. Electrodes are there that are placed under the skull but not inside the tissue. This is called as under the skull, but this is called as semi-invasive. This is called as semi-invasive. Provide better signal quality than non-invasive BCI. This provides better signal quality than non-invasive. Why? Because here we are implanting this particular electrodes inside the brain, but that is not we are not going for any surgery, but just we are going to implant that particular electrodes inside the brain. Now, application: epilepsy monitoring, early stage prosthetic control research. In that particular application, we use this particular semi-invasive BCI devices. Next, another one is non-invasive BCIs. What we are doing now, whatever the applications we are using that are non-invasive BCI. Non-invasive BCI means we are not going to implant anything on the brain. We are not going to implant any electrodes under the brain or under the skull, or just we are going to use that particular EEG device over the surface of the skull. We will touch that particular cap with the your brain. So that is called as non-invasive BCIs. It use external sensors like EEG, FNIRS to record brain activity through skull. Next, here, safe and widely accessible. It is safe. It is very safe. There is no problem with this type of non-invasive BCI. Why? Because it is we are not implanting anything under the brain. So that's what it is very safe. There is no problem with this type of BCI. There is no problem with this type of BCI. That is the one advantage of this particular BCI. Next, importance in various applications. What are the application we are going to use in this particular brain-computer interface? What and where we are going to use? In effective computing, one is the area. Mental health monitoring. This is a very much interested area, which is aligned with our FDP, which is our topic of the FDP. So mental health monitoring. For example, one particular person yesterday, the sir, most of our speakers discussed regarding sleep monitoring. Yesterday, Ganesh Nayak and previous second day, our Bapiraj sir told that here some they discussed regarding sleep monitoring discussion. So, so in that cases, some psychological or some mental related problems, we use this particular EEG device. Mental health monitoring also, we can use this particular device, mental health monitoring. Next, another one is neurofeedback and self-regulation. So in the neurofeedback mechanism also, we use this particular device, neurofeedback and self-regulation. For example, to control your devices or prosthetics or something, we use this particular device. Next, another one is assistive technologies. What is assistive technology? This is also very important. Recently, we got one funding projects under SERB. Recently means in 2019, that is completed. Okay, but in that project, we are going to control the mouse without using brain-computer interface application. So in that, what we have to do, we use the same EEG, and that EEG will take the data from 32 channel EEG, that and we pre-process the data, feature extraction. Then after that, that will be translated into the commands, and without without any person who suffers from neurodegenerative problems like ALS or any problem, who cannot move his hands or legs or what, in that case, we can use this particular applications. These assistive technologies can be useful. Next, human robot interaction. This is also human machine interface, where here one particular person here, he directly without giving any signals, he will directly inform to the he can control one particular devices. Another one is market research and advertising. So this is also one of the important area we can use EEG. So you may get the doubt that, sir, how we can use this brain computer interface in market research and all those things. So anybody got any idea how we can use this brain computer interface in market research? Anybody? Anybody? So we have one device that is called as eye tracker. That eye tracker means it detects the movement of the eye, where we are looking, what time we are looking, how much time, how is our perception about that particular thing. First, in a human psychology, what is the first thing generally usually react to the to our interested things? Our eyes usually reacts. So if you look at that particular thing more amount of time, that indicates that you are interested in that thing. So in that way, the market here, they will analyze that here you are interested in that particular product. So in that way, we can utilize this brain-computer interface in market research and advertising. Next, education and training. Usually in education and training, also in virtual reality, in augmented reality, also we can use by integrating this brain-computer interface with augmented reality, virtual reality. We can use this particular brain-computer interface devices. Next, another one is entertainment and gaming. In the entertainment and gaming, also we can use this particular devices using what just now I told, augmented reality and virtual reality. Next, clinical diagnosis. Clinical diagnosis also we can use. So in clinical dialysis, mental rehabilitation centers, we can use this particular devices, BCI devices. Another one is stress management. In stress management also, we can use this particular device. Because it can identify your signals, EEG, it can identify your stress levels as well as your sleep, your physiological signals. It can easily identify, and we can easily find. Participants, some participants are, who is that? Okay. No, okay. Now here, our next topic is how this BCI works. And the BCI, how it will works mean, it will not directly take the signal from your brain and it will not directly give it to the computer. Not like that. If I am sitting in front of our computer, it will not directly take the signals from my brain. If I keep one EEG device, it will not directly take from your brain and it will not give it to you the computer. It's not like that. So we need some methods and some paradigms. That methods are called as paradigms. That paradigms we have to use here.
प्लस माइनस क्या होता है? फिर आपको मालूम है क्या फिनिश होगा?
Yes, yes. Participants, please mute your mics. Now BCI paradigm. So what are the methods we can use to identify? What are the methods we can use? That methods are called as paradigms. Paradigm is a method to identify the signals in the brain. So we have to follow some procedure or method to detect the signals in the brain. So that is called as a paradigm. How and what type of data will be recorded? So there are different types of paradigms we normally have. One is SSVP. That first one is SSVP. That is steady state visually evoked potential. Next, second one is motor imagery. Third one is P300. Fourth one is hybrid. So first one is steady state visually evoked potential. Second one is motor imagery. Third one is P300. Fourth one is hybrid. Hybrid means the combination of any above two methods. So first, I will discuss about what is steady state visually evoked potential. So steady state visually evoked potential, shortly we can call it as SSVP, where EEG signals recorded is the direct resultant of the visual stimuli presented. So there are some visual going to be present on the screen. So for example, it's like blinking, just like it is one particular thing is blinking on the screen. Now it is flickered with some frequency. It is, if you take anything, you have a screen in front of you, it will just, here it is flickering. For example, it is flickering, then it what frequencies. So there are different flicker frequencies are there. So if you look at one particular flickering frequency, that results one type of signal. If you look at another flickering frequency, it will generate another type of signals. That is the like that we can extract the signals. That is the steady state visually evoked portions. Visual stimulus will flicker at a different frequency in alpha range, and this allows separation of the stimuli. So that is called as a steady state visually evoked potential. So now this particular thing, whatever the signals are there, that will be flickered at different frequencies. That will be flickered at different frequencies. That frequencies here you can classify. That is called as a visual steady state visual evoked potentials, SSVPE. So the advantages, it is SSVPE, no training needed. That is the first advantage. Not much training is required. Second one is it is high accurate. Second one is it is high accurate. Disadvantage. Coming to the disadvantages, here irritation due to flickering stimulus. So, if, for example, if anything flickers, that means blinking. Flicker means it is blinking with some frequencies. For example, here it will flicker with like this. Something flicker with some frequency like this, like this. Some flicker with some different frequency. Anyway, one patient is also a patient. Only patients can use this brain-computer interface devices. If patient sitting in front of that flickering and if you see that particular device or that flickering machine, then what will he feel? Usually feel irritated. So that is the one major disadvantage of this particular SSVP paradigm, and also high latency. Next, another paradigm is motor imagery paradigm. Motor imagery is a simple paradigm. So just now we have discussed where one particular person imagine is closing. Right hand is closing, and releasing. When he feels or imagine or visualize, if he is closing that hand, it will generate one particular type of signal. If he imagine is opening his hand, it will generate another type of signal. In the similar way, if he imagine his left hand closing, it will generate one particular type of signal. If he is imagining his left hand is releasing, it will generate another type of signal. So this is called as motor imagery signal. Regarding advantage, it is less time taking in term of training. It takes less time for the participants, those who are under experiment. That is a one advantage. Next, it provides more realistic approach. It is a realistic approach. Why? Because even though he is a patient, visualization is not a problem for him. Just he is visualizing that I'm moving my left hand, moving left hand. Just visualizing that left hand, and visualizing right hand. I'm moving my right hand, right hand, right hand. So there is no problem with this type of method. Disadvantage: motor imagery has high latency due to dwelling time. So because of some, why? Because he has to imagine. Visualization will not happen within short span of time. It will take some time. If you want to visualize something or some thing, it will take some time or some amount of time. So that is the major disadvantage of this motor imagery paradigm. It is visually here it is shown like this. So left hand, right hand, left foot, right foot is visualizing that. I'm opening my left hand, I'm opening my left hand, opening, just he will visualize left hand. And I'm moving my right hand, moving my right hand, moving my right hand. Like that he will visualize. I'm moving my left foot, I'm moving my left foot, is visualized like that. I'm moving my right foot, I'm moving my right foot, like that also will visualize. So based on that, it will generate some signals. Now, Here I am going to give you one best example of motor imagery paradigm. Look at this. Just is visualizing. Nice music. But what we can extract from this video is that one particular here one person is there, is unable to.
ಎರಡು ತಾಸ ಅವ್ರು ಹಾಕಿ ಹಿಡ್ಯಾಕತ್ತಿರ್ತಾರ ಹೆಂಗ್ ಸಿಗ್ತಾನ ಹಂಗ್ ಚೇಂಜ್ ಮಾಡ್ಬಿಟ್ರ ಇಡೀ ದಿನ ಅದ ಆತು
Yes, here is visualizing that he is moving a right hand, moving left hand. So when he is visualizing about that he is moving right hand, means this particular machine or that particular thing, it will move this way. Once again, you just look at this. Okay. Next, another type of paradigm is P300 paradigm. So what is P300 paradigm? This is also called as oddball paradigm. So it is a positive deflection in the signal after about 300 milliseconds of the presentation of the stimulus. P300 means a deflection after 300 milliseconds, which is positive. P indicates is positive. And some another type also there. N is also there. N means negative. P means positive. If you observe this, any odd thing happens. For example, suddenly some person just shouted. What will happen? In my brain, there is a huge spike in the signal. Why? Because that shouting is odd to me. Anything which is not a normal thing happen, usually there is a spike in your spike signal in the brain. So that is called as a P300. Here, what is P300? Just now I given one example, but that will not happen naturally. Why? Because no one will shout and give a diffracted signal, positive P300 signal. It will not like that. So we add some different experiments are there. What is that? In that one is oddball paradigm. So here there are different things will happen. In that, one odd thing also happens. When odd thing happens, your brain reacts, or in your brain, some deflection will happen. So that is called as a oddball paradigm or P300 thing. So this P300 paradigm is mostly oddball paradigm, where this positive deflection is the result of the identifying the target among distractors. Next, P300 advantages. It is high accurate, as well as training is not required. Training also not required. Much training is not required, and moreover it is high accurate. So what are the disadvantages of this particular method? So it is time consuming paradigms. User has to focus on the selection of for a long time for classification of P300 responses. It is a time consuming. Why? Because normally odd things will not happen regularly. So this is P300. Hybrid BCI paradigms. Hybrid means combination of two or more paradigms. That is called as a hybrid paradigms. Hybrid paradigms are typically used to do more complex tasks in less time. So if it's not works with only one type of particular paradigm is not suitable for that particular application, we can mix for our convenient. What is the problem in that? We can easily mix the different paradigms. That is also hybrid paradigm. Hybrid paradigm disadvantages. Hybrid BCI paradigms provides better accurate than the individual paradigms of the hybrid. Hybrid paradigms can be used in more complex tasks. Hybrid BCI paradigms provide better accurate than the individual paradigms of the hybrid. Hybrid paradigms can be used in more complex tasks. So what are the advantages? Hybrid BCI paradigms are more confusing and difficult to train the individual paradigms of the hybrid. So here hybrid of look at here. SSVP as well as P300. Both are hybridized. Look at here. This is regarding hybrid BCI. Hybrid means it is we can use two or more paradigms. It is a combination of two or more paradigms. That is called as a hybrid paradigm. Now, how this BCI can be used in natural language processing? There are different applications are there, but in our topic, we are going to discuss about natural language processing. Natural language processing means processing of the natural signals. What are the natural signal? Speech, okay now, words, these are the natural signals. So here there is a signal acquisition. Usually we take the signal from the brain. For that we use EEG device. Then the signal will be given to one classifier. We have to train one particular model. That model gives some classification that again will be translated into words. They where natural language processing comes into the picture. Brain signal that can be translated into the words by using natural language processing techniques. Here I am not talking much about the natural language processing, but how we can use BCI in natural language processing applications. So this review paper published in IGI Global Publishers. Along with my BTech UGR students, we have published one paper in this concept. So here, this is the brain signal. This brain signal will be acquired through EEG that will be given to the classifier. This classifier will be given to one particular signal processor, and that will be converted into the text. Now, look at here. This person is unable to speak, unable to write. Is unable to write. Why? Because it's just simply is suffering from neurological disorder problem. Let us assume that. Now, what we have to do? We have implanted one particular EEG device here. We have implanted one particular EEG device here. That EEG device, and what it will do here, that EEG device here, that will be translate is signals, thoughts, or is thoughts into commands. What are that commands? That commands in the form of text. That is called as a brain to word. That is called as a brain to word. Here, brain signals that will be translated into the word. That is called as a brain to word thing. Now, here, this will be translated into the words. A means, for example, A. Slowly, it will write B. It will write C. It will write D. It will write D, E, F, G, H, V, U, H, I, J, K, L, M. Like that, it will write. So this is regarding natural language processing. Now, in a similar way, we can use this brain-computer interface in assistive technologies also. In assistive technologies, what are the assistive technologies we can use here? Now I told that in the control of mouse. In the controlling of mouse also, we can use this particular brain-computer interface. So here, first, what we will do, we will capture the brain signal. If it is a real time, we will take from the EEG device, or if it is a simulation part, we have to take it from the existing data set. Then after that, we use signal processing algorithm, which is very, very important. Then this signal will be given to some signal processing algorithms. Signal processing means some artifact removal techniques. Where we use some artifact removal techniques. Then feature extraction. Feature extraction means here feature extraction. Then after that, classification. Then your application interface. Then followed by which can be given to some devices. This is called as a implementation of your thing. So we can control the devices. We can control the devices like smart home, robotic arm, wheelchair, drone control, web console control, etc. So with this, we can control the external device here. So in that way, we can use this brain computer interface in assistive technologies. Here methodology. For that, we use capturing of brain signals. We take some existing data set, which is from BCI competition data set 2A and 2B. So 2 days back, Rahul Chaurasia sir told that the begin for the BCI experiments or BCA work, we have to start with some existing data sets. Existing data set in that one standard data set is BCI competition data set 2A and 2B. I think Shankar asked this question. Shankar is there? Next, after that, we have to capture the signals. Then we will apply the signal processing algorithms. Then feature extraction. Then classification using MDNN algorithm. Then we will give it to the application interface. Then we will give it to the application, which can be used to control the cursor. So for that, we use some in the pre-processing stage, we use some filter banks. So this work done by our research scholar Srinath. So he published several papers. We, along with my scholar Srinath, have published some papers in this. One is there we have to use some filter banks, FCIF algorithm for class iterative filtering. There we have to use. So in that modified deep neural networks, we have to use as a classification technology, a modified DNN classifier used for motor imagery classification with 4 class BCSP features. The deep neural network architecture is adapted to handle the input data from FCFBCSP, designed for efficient and accurate MI signal classification. We have proposed one method. The advantage of the proposed method is which is the efficient and accurate for MI signal classification. Then convolution layers for spatial feature extraction, fully connected layers for high level feature learning and classification, dropout regulation to prevent overfitting. So in that, we need to use pre-processing algorithms which can remove noise and artifact from EEG signals. We use some feature extraction techniques which can extract discriminative features for classification. We use modified DNN classifier, classify pre-processed signals into motor imagery tasks. And after that, we need to train the classifier on labeled data. Testing, evaluate the classifier's performance on unseen data performance. After that, performance evaluation, analyze classification accuracy and other metrics. So this is the workflow diagram. In that, first we have to pre-process the data. Then we have to take the feature extraction, then followed by modified DNN classifier, then training, then testing, then performance evaluation. So these are the steps in implementation of modified DNN classifier for cursor control. So for that, the data set that we have taken is from BCI competition for dataset 2A and dataset 2B. It can be downloaded from this website. You just check or copy this website www.bbci.de/competition/4. Then here how we have taken the dataset. The dataset is the description of the dataset is here we have taken from 50 individuals. Participant met inclusion criteria such as age, cognitive ability, and absence of neurological disease that we have taken care. This is actually existing standard data set. EEG, next after that, experimental setup and protocol testing, emotive insight and EEG, emotive insight EEG headset was used for data acquisition. It has 5 EEG channels, which consist of 128 Hz sampling rate and built-in amplifiers. Dry EEG electrodes were used. The headset also includes accelerometers and gyroscopes for capturing head movements. So these are the EEG signals when we are captured from a brain. These are the results we got. There are 4 classes. Why? Because we use motor imagery. There are 4 classes: class 0, class 1, class 2, class 3. Class 0 indicates right hand. Class 1 indicates left hand movement. Class 2 indicates foot. Class 3 indicates tongue. Now, class 0 predicted 197. Predicted class 0, 197. Predicted class 1, 1. Predicted class 2, predicted class 0, 3. So actually, if it is a class 0, means it is predicted 197 as it is. Instead of how many samples here? 197 plus 3, that means 200. So only these 3 samples are wrongly predicted as a class 1 and class 2. If you look at class 1, that means left hand movement, left hand movement. Here, predicted class 0 is 2. In that, predicted class 0 is 2. Predicted class 2 is 1. Predicted, that is false. Predicted class 3 also 1. That is also false. Predicted class 0, 2, also false. Why? Because it is actually class 1. Hence, 176 exactly predicted. Next, coming to class 2, that means foot. So here, class 1, class 0, wrongly predicted 1, class 3, wrongly predicted 1. Class 3, tongue, that means it is predicted 0, predicted class 0 as 0, predicted class 1 as 2, predicted class 2 as 3, predicted class 3 as 185. So these 5 samples are wrongly predicted. This is called as true or false negative, false positive, sorry. Now, experimental results. So if you compare with our existing DNN, deep neural networks, as well as modified DNN, so there is a accuracy is almost same, precision also same, recall same, F1 score is also same. Now, proposed modified DNN. If you consider modified DNN, then compare with DNN, here the accuracy 98.575, SVM baseline it is 95.2, KNN baseline 93 point. So there is a much difference between SVM and modified DNN. Here, this is the comparison performance with other existing methods like SVM, KNN, CNN, LSTM. These are the, when we compare with that, the accuracy is here, this is our modified DNN, existing DNN, SVM, like this, there is a comparison. in precision also. This is the first flow graph. It shows accuracy. Second one, precision. Third one is recall. Fourth one, specificity. Next, performance comparison. Regarding performance comparison, here we have different methods there, which is 95% in modified DNN, DNN, as well as CNNB, like that. There are different methods. Then compared to experiment results. These are the experiment results. This is the cursor. Here cursor position, cursor traces, average trace, trial 1, trial 2. So this is the thing we have, what we have observed from the graph. So this is regarding application of brain-computer interface using modified DNN algorithm. So here usually we'll get good results. Why? Because we have used some advanced modified DNN algorithms. So this is work done by our scholar. So here our proposed method is also having some strengths as well as some limitations. The strengths, coming to the strengths, it has high accuracy, efficient response times, balanced revolution metrics, robustness. These are the strengths of our proposed model. Next, coming to limitations, it needs further research on personalization, long-term usability, and the user interaction enhancement. We need to do some user interaction point of view. We have to think about that. So this is regarding strengths and limitation of our proposed model. So challenges and future directions. So usually it is non-stationary artifacts and mode mixing. One is there is a future research also there in artifact removal techniques and enhancing machine learning algorithms for different application. Of course, anywhere we have some future development, even though if we do some 99, also 99.9% also there is a chance hope for 1%, 0.1 improvement. There is always scope for improvement. So even though not only in the direction of pre-processing in terms of feature extraction, classification accuracy, and application point of view also, there are different things will be there. Yes, dear participants, are you able to listen my voice? Yes. Lakshman.
Yes, sir.
Okay. Audible. My voice is audible.
Yes, sir. Yes, sir. Everything is clear, sir.
Clear, huh?
Everything is clear, sir.
Okay. Thank you. Thank you. So now coming to, we use 4-class iterative filtering and 4-class filter bank, common special filter pattern for EEG signal processing. Then the classifier design is utilize a modified DNN network for motor imagery classification, train and validate the DNN for accuracy and speech in cursor control. Then coming to feature extraction, apply FC, FB, CSP for feature extraction, capturing discriminative features for real-time task. Integration and testing, we integrate FC IF with the FC FBCSP and the modified DNN into a comprehensive BCI system. So here we used some deep neural network method, and then we have performed better results compared to the existing methods. And this is regarding one of my scholar work. Just we have recently is going to give his presentation on next week most probably. So almost his work completed, and his